Again, I'll end up putting it on YouTube, so please type your name here for the attendance. So yeah, so if you can write your name into the chat at some point today, because it's very important to do it today, because Sange is not here today, and Sange usually takes attendance. So if Sange is not taking attendance, the best way to make sure that you're counted for the data for the next time is to type your name here into the chat. And then on the recording, we'll have a record of everybody who was here. Okay, so if you have some time now or at any time during the class, please type your name. Please type your name into the chat so that I know that you're here for the attendance. Okay, so welcome everybody. I hope everybody had a good week and is getting ready for a good weekend. I hope you all got counted for the census last week. Maybe not for this semester because it's not really related to what we're talking about, but maybe for a future semester or a future year, we'll talk a little bit about sampling and surveys in statistics and how you can get, good information even from only sampling a few people. So we might do maybe some more advanced statistics and statistical inference. Not this semester, but maybe that'll be a good topic for a later semester for the workshop. Okay. Okay, great. So just a reminder again, if you haven't done so yet, please type your name into the chat so that we have a record that you were here. If you don't type your name in, we may not have a record that you attended. And so we want to make sure that you type your name, especially if you're not using your real name on your profile. So I see there's 3.14159 here. And I think everybody else is using their real name, but again, please type it in if you haven't done so already. And I'll try to maybe do some typing in for the people who aren't doing it, just to make sure that we have everybody. Okay, because we don't want anybody to not receive data who is supposed to receive data. Okay, great. So we're going to talk a little bit more today about these matrix transformations. So first, let's just go talk about the homework. Remember, just to recall, well, maybe let me do the recalling before we go over the homework questions. So remember, what we talked about last time was this matrix vector multiplication. And so we started with an m by n matrix that we called A, and then we multiplied it, in this case, by a vector, an n by 1 matrix. This is what we call a column vector. And it turned out that the product was an m by 1 matrix, which we also think of as a column vector. And one way of thinking about this idea is to think about multiplication by A as being a function, where the input is a size n vector. That's what we start with. And the output is a size m vector. Okay, that's what we get after doing the multiplication. Okay, so and as a matter of notation, we just write Rn means the space of all size n vectors, and Rm is the space of all size m vectors. And what we see is that multiplication by A gives a function from Rn to Rm. Okay, and this type of function is sometimes called a matrix transformation, or it's sometimes called a linear transformation. Okay, and we saw some examples of this the last time. So Saley is having trouble seeing my screen. Can people see my screen? Can people see the notes? Yes, okay. Okay, so Saley, I think the problem is on your end. You may need to change something with the Zoom setting on your phone in order to see it, because I think it's coming across to everybody. Let me just type. It's just here. Okay, great. Okay, good. If everybody can see the note, then we'll do that. Okay, so for the homework, we have a couple of just exercises to try to remember this. So the first one is straightforward. So we want to evaluate the image of a certain vector under the matrix transformation given by this matrix. And so this is just a fancy way of saying evaluate 1, 4, 1, minus 2, 0, 0, and 3, 2, minus 3, multiply this by 3, 1, 2. And remember that we have two ways of doing these matrix vector products. You can just do the standard matrix multiplication, the way we defined it, or you can use this column method. And maybe we'll use the column method for this question. So remember what the column method is. We go through all the entries of the vector, the 3, the 1, and the 2, and we take 3 times the first column, and then 1 times the second column, and then 2 times the third column, right? We go 3 times the first column, and 1 times the second column, and then 2 times the third column, and then we add it all up. So does anybody want to do that? Okay, I mean, I can do it for now. I'm getting warmed up, right? So what we can do is we take, this is the same as 3 times the vector 1 minus 2, 3, plus 1 times the vector 4, 0, 2, plus 2 times the vector 1, 0, minus 3. And so we can write this as 3 minus 6, 9, plus 4, 0, 2, plus 2 times 1, 0, minus 3 is 2, 0, minus 6. And when we add these vectors all up, we just add them position by position, and we get 9 minus 6, and then 9 plus 2 minus 6 is 5. Okay, so this is the answer that we get. So if we start with the vector 3, 1, 2, and then we apply this matrix, this 3 by 3 matrix here, then when you multiply them together, you get 9 minus 6, 5 as the output. All right, Saley, good. Okay, I'm glad you can see it. Great. Okay, so this is how, this question is just saying multiply this matrix by this vector, and the answer we get is 9 minus 6, 5. Okay, any questions on this? Okay. No questions, it's clear? Okay. Great. Okay. All right, so let's go to the next question. All right, so the next question asks, is there a 2 by 2 matrix such that whenever we input a vector xy, the output vector is x plus 1, y plus 1? Okay. So can we, remember we talked about certain matrices last time that did certain things. We had a matrix that doubled every vector. We had a matrix that reversed every vector. So here is a question we're saying, is there a matrix so that when you multiply it by a vector xy, the result is that you add 1, 1 to the vector xy. So you increase both coordinates by 1. Did anybody, even if you didn't fully solve the question, does anybody have a guess whether the answer is yes or whether the answer is no? Do you think we can find a matrix like this, or do you think we can't find a matrix like this? Okay. Well, so here's the idea. So the answer is no. Okay, so you can't find a matrix. You can't find a matrix that that satisfies this. And the reason is, what happens if you plug in x, y equals 0, 0? So what happens if you plug in x, y equals 0? So if we say that A, our 2 by 2 matrix, is equal to, we call it A, B, C, D. Okay, well then A, B, C, D times 0, 0 is equal to what? No matter what A, B, C, and D are, what do you get when you multiply the matrix A, B, C, D by the matrix 0, 0?
The result is a zero matrix.
The result is the zero vector, exactly. Right, thank you, Rufus. So, right, the result is always 0, 0. But what's the question asking for? It's saying that if you plug in x, y, you should always get x plus 1, y plus 1. But here we saw, so no matter what matrix we plug, so no matter what matrix we use, we use for A, we always have that A times 0, 0 is equal to 0, 0, right? No matter what. So, but the question asks, is there a matrix that if we plug in 0, 0, we would get 1, 1, right? Because the matrix, it's saying, do we have a matrix where if you plug in x, y, you get x plus 1, y plus 1? So if you plug in 0, 0, can you get 1, 1? And the answer is no, right? We've seen every matrix A, if you plug in 0, 0, you get 0, 0. So we cannot get 1, 1 by plugging in 0, 0. Okay. So this means there is no such matrix A. Okay, you can't find a matrix that sends every vector xy to x plus 1, y plus 1, because that would mean it would have to send 0, 0 to 1, 1. And you just can't do that, right? That no matrix is going to send 0, 0 to 1, 1. Okay. Okay, so any questions on this?
Yeah, the symbol arrow square means what? Real number?
Oh, yes, it means, so R2 just means, this just means the set of all vectors where the vector has size 2 and each entry is a real number.
Okay.
So the 2 means that it's a size 2 vector. It's got 2 entries. And the R means that the entries are real numbers. Okay. Yeah, so this is what we had over here. Just as a matter of notation, we write Rn for the space of all size n vectors, and we should say with all entries in this course, all our entries are always going to be real numbers. Yeah. Okay, so all entries are going to be real numbers in this course. No, 0 is a number, that's fine. So 0 is a real number, that's not a problem. The problem is the question, so this is to Sally's question in the chat. We're saying, are we saying 0 is not a number? We're not saying that. 0 is definitely a number. What we are saying is that you cannot take 0, 0 to 1, 1, right? And so this question is asking for a matrix that when you input 0, 0, the output would be 1, 1. And what we showed is that you can't do that, no matter what matrix you use. If the input is 0, 0, the output will always be 0, 0. So you can't take 0, 0 to 1, 1.
Okay.
Okay, so does that answer your question?
It is clear.
Okay, good. Okay, so let's do the third problem then. So this is a kind of interesting one. So this again, it's a kind of, you have to think a little bit to solve this. So I'm not telling you, I'm saying we have a 3 by 3 matrix A, and I'm not telling you what the matrix is. I'm just telling you that it satisfies these two properties. That if I multiply A by 1, 2, 3, I get 1, 4, 7. And if I multiply A by 2, 1, 5, I get 2, 3, 0. And the question is, what do I get when I multiply A by the vector 3, 0, 7? Okay, and we have to be able to do this without knowing what A actually is. And the rule that we want to use is a rule from last time where we know that A times CV plus DW, you can write this as C times AV plus D times AW. Right? This is the rule that we have from the last time. Okay. Okay. So this is the rule. Okay. So the idea is, well, if we know what A does to 1, 2, 3, and we know what A does to 2, 1, 5, well, maybe we can figure out what A does to 3, 0, 7 by writing it as a kind of combination of 1, 4, 7 and 2, 1, 5. Right? So if we let V equals 1, 4, 7 and W equals, oh, sorry, not 1, 4, 7, 1, 2, 3 equals 1, 2, 3, and W equals 2, 1, 5, well, can we write 3, 0, 7 in the form CV plus DW? Right, that's what this is asking. Can we write this vector 3, 0, 7 in this form? Right? Because if we can do that, then we can figure out what A times 3, 0, 7 is. Yes, question, Harris? Or Harris?
Il a rien.
Hello?
Vous voulez qui?
Okay, again, please mute yourself unless you're asking a question or answering a question. Okay, so can we write this in the form CV plus DW, right? So what we're trying to do is solve, so this is the first step. We want to solve C times 1, 2, 3 plus D times 2, 1, 5 equals 3, 0, 7. Right? Because if we do this, then we can write 3, 0, 7 in the form CV plus DW, and then we can apply the rule. Okay? So how do we solve this? Well, you can either guess and check, or you can just write down a system of equations in each coordinate, right? So this is the same thing as saying C plus 2D equals 3, and 2C plus D equals 0, and 3C plus 5D equals 7. Right? So there's lots of different ways that you can solve this, but maybe we could do a substitution. You do a substitution here, maybe in the second equation, you would get that D equals minus 2C. Right? This is what we do if we substitute in the second equation. And so then what do we get? We get C plus 2 times minus 2C equals 3, and 3C plus 5 times minus 2C equals 7. And what this tells us is that minus 3C equals 3, and this says minus 7C equals 7. Right? 2, 1, 5 are the coefficients here, right? This is the 2, this is the 1, this is the 5. Right? I have C times this vector plus D times this vector equals 3, 0, 7. So I write an equation for each coordinate. And I get C plus 2D equals 3, 2C plus D equals 0, and 3C plus 5D equals 7. Okay. And if you solve this system with by making a substitution, D equals minus 2C, what you end up getting here is that C is equal to -1. And then since D is equal to -2C, D is equal to -2 times -1, which is 2. Okay, so what that tells us is that -1 times 1, 2, 3 plus 2 times 2, 1, 5 is equal to 307. Okay, so this is the first step, right? We've written this 307 in terms of our input vectors, right? In terms of 1, 2, 3 and 2, 1, 5. Okay, so the second step is to use the rule. Right? So what's the question asking for? It's asking for A times 307. Oops, did you do that? Sorry, wait, what did I do there? Yeah. So it's asking for A times 307. So we have that A times 307 is equal to A times -1 times 1, 2, 3 plus 2 times 2, 1, 5, which by the rule is equal to -1 times A times 1, 2, 3, and then plus 2 times A times 2, 1, 5. And now, but we're given, we know what A times 1, 2, 3 is. It's 147. And we know what A times 2, 1, 5 is. It's 230. So what that tells us is that we're just getting -1 times 147 plus 2 times 230. And this, when we add these vectors up, we end up getting that's 3, and then 2, and then -7. Okay, so this is going to be the answer. 3, 2, -7 over here. So maybe this is a little bit messy to look at. So let me try to separate the two steps from each other over here. So we have our first step over here, which is trying to write 307 in terms of a combination of 1, 2, 3 and 2, 1, 5. That's what we did here. We saw that 307 was -1 times 1, 2, 3 plus 2 times 2, 1, 5. And then for the second step, we use the rule and the fact that we could write it as this combination to get that A times 307. Well, if instead we write it as this combination, then we can use the rule, which lets us break this apart and lets us rewrite this in terms of A times 1, 2, 3 and A times 2, 1, 5. Okay. And when you put that all together, you get the answer, which is going to be 3, 2 -7. Okay, so it's a bit of a tricky problem. You really have to do it in these two steps. Okay. So any questions on that? Okay. All right. Okay. So, all right. So let's talk about what we're going to talk about today. So we already talked about this matrix vector multiplication. And if you remember what we did last time, so today we're going to talk about geometry in the plane. So we're going to specialize to the case of 2x2 matrices. Okay. So we're going to talk about 2x2 matrices where the input is a vector in R2, so it's of the form xy, and the output is also in R2, so it's also of the form xy. And what we want to understand is how to encode some standard geometric operations on vectors, how to encode them with matrices. And we did this, some small examples, last time, right? We saw last time that the matrix 0, 0, 0, 0 sends every vector v to 0. That the matrix 1, 0, 0, 1 sends every vector v to itself. The matrix 2, 0, 0, 2 took every vector v and doubled it. And then the matrix -1, 0, 0, 1 takes every vector v and reverses it. Okay. Takes every vector v and reverses it, right? So we saw that these matrices encode geometry, right? They encode things that are very much like something that you can see with geometry, like taking a vector and reverse it. That's something that can be described using geometry. Taking a vector and stretching it by a factor of 2 can be described using geometry. So today we're going to talk about 3 of these transformations. One of them is called dilation, one is called rotation, and one is called reflection. We might not fully get to reflection, but we'll do our best. Okay, so looking at what we have here, we saw that 1, 0, 0, 1 sends every vector v to itself. 2, 0, 0, 2 doubles every vector v. So here's the first question, and this is called a dilation. So let's say that C is a scalar. So what is the matrix that multiplies every vector by C? So that is, we want a matrix that sends every vector v to CV, right? So we want a 2 by 2 matrix A with the property that if I take A times any vector v, what I end up with is C times v, where C is just some scalar that I give you. So based on what we see over here, 0, 0, 0, 0 send every vector v to 0. 1, 0, 0, 1 sends every vector v to v. 2, 0, 0, 2 sends every vector v to 2v. Here, minus 1, 0, 0, minus 1 sends every vector v to minus v. That's what it means to reverse. So what matrix is going to send every vector v to C times v, where C is some scalar? It might be 5, it might be 7, whatever it is. What matrix is going to do that for you? Anybody have an idea what matrix we should? So for instance, if I wanted to multiply a vector by 3, what matrix should I use for that? Yep. So if I want to multiply a vector by 3, what matrix should I use for that? And we saw that 2, 0, 0, 2 multiplies every vector by 2. So what do you think is going to multiply every vector by 3? Okay, well, it's going to be 3, 0, 0, 3 is going to multiply every vector by 3. And 5, 0, 0, 5 is going to multiply every vector by 5. And in general, the matrix that we want for this, the matrix is, in general, it's going to be C, 0, 0, C is going to do this, right? And how do we check this? Well, if I take C, 0, 0, C, and I multiply it by any vector x, y, well, using the column method, this is x times C0, x times the first column, plus y times 0c, that's y times the second column, and this is exactly xc, yc, and this is the same thing as c times xy. Okay. So I'll box this. If we start with this matrix and we multiply by xy, then the result that we get is c times xy. Okay. So this is the 2 by 2 matrix that we want. The matrix that we want is C0, 0, C. Okay, and that multiplies every vector xy by this scalar c. Okay, and what we saw on the previous page are all the examples of this. This one right here is the case c equals 0. It multiplies every vector by 0. This is the case c equals 1. It multiplies every vector by 1. This is the case c equals 2. multiplies every vector by 2. And this is the case C equals -1. It multiplies every vector by -1. Okay, but this works for any constant C. Okay, any questions on that? Okay. All right, so dilation is pretty straightforward, right? We just use this matrix C0, 0, C, and it works. It multiplies all vectors by C. So now I want to do something that's a little bit more involved. So this is rotations around the origin, okay? So let's say that we have a vector whose angle from the positive x-axis measured clockwise is theta, okay? And let's say that its magnitude is equal to r. So let me draw it like this. Okay. So let's say this is my vector. This is my vector v, and it has some angle theta from the positive x-axis, and its length is r. Okay? So if we have that the magnitude of v is equal to r, then one of the things that we've seen so far, right, is that we can write if we want to write v in terms of coordinates, we can write it, if this is a right triangle with side r, then this side here is going to be r cosine theta, and this side here is going to be r sine theta. And so that means that if you're trying to write down the vector v in coordinates, well, the x coordinate is r cosine theta, like this, and the y coordinate is r sine theta, exactly like this. Okay. Once again, by the way, a reminder, if you have not done so, to please type your name into the chat, okay? If you don't type your name here, then we will not have a record of your attendance. So we need you to type your name into the chat. Okay. So, all right, so this is our vector. It's r cosine theta, r sine theta. Okay. Okay, so what can we find a matrix that takes any vector like that and then rotates it by another angle alpha further counterclockwise, right? So what would such a thing do? We would start with the vector v over here. This is theta. And then let's, sorry? Okay. So then what would we do? We would rotate it a little bit. So this is going to be another angle, we'll call it alpha. And then we have our new vector, which we'll call w. So w is the results of rotating v by an angle alpha counterclockwise around the origin. Okay, so this is what we get if we rotated an angle alpha. And so the thing to realize is that if we look at the angle that w makes with the x-axis, it's not theta, but it's now theta plus alpha, right? So the angle that w makes with the positive x-axis is theta plus alpha, right? And so that means if we want to write w in coordinates, let me just do it right here. W, well, it has the same magnitude as v, right? Because it's just rotated. That's not going to change the magnitude. But now it's pointing at a different angle. So the angle that it's pointing at is not theta anymore, but it's now theta plus alpha. So W here is going to be R times cosine of theta plus alpha and R times sine of theta plus alpha. Okay. This is what W is. And let me just add in a page where we recall these trigonometric formulas. So I'm going to add this on a new page. So recall cosine of theta plus alpha. If you remember the formula, this is equal to cosine theta cosine alpha minus sine theta sine alpha. And sine of theta plus alpha is equal to sine theta cosine alpha minus cosine theta sine alpha. No, sorry, plus cosine theta sine alpha. Okay, so these are the so-called addition formulas. For sine and cosine. Okay. So what does that tell us? That tells us that if we have this vector v, r cosine theta, r sine theta, and we rotate it by alpha, we get this new vector, r cosine theta plus alpha and r sine theta plus alpha, which if we then simplify it using these trigonometric formulas, we end up getting, so what this tells us is that W, what is this vector W? Wait, what did I just do? This vector W is going to be equal to R times cosine theta cosine alpha minus sine theta sine alpha. And then down here we have R sine theta cosine alpha plus cosine theta sine alpha. Okay, so this is our new vector. Okay, so what we're really looking for is a matrix that sends the vector r cosine theta, r sine theta, remember this is the vector that we called v, to this new vector w, which is given by these formulas we had on the last page. So it goes r cosine theta cosine alpha minus r sine theta sine alpha, and then r sine theta cosine alpha plus r cosine theta sine alpha. Okay, so this is what we're looking for. We want a matrix where v is the input, v is some vector pointing at an angle theta, and w is the output. And w is the same vector, the same length of vector, but now pointing at an angle theta plus alpha instead of just an angle theta. That means is that we're rotating everything by an extra angle of alpha. Okay, so we're looking for a matrix that takes this vector v as the input and spits out w as the output. Okay, any questions? Any questions so far? Okay, no questions on this? Okay, so now what you can do is you can basically guess. And the guess is not so easy. But let's say I take the following matrix. If I take A to be cosine alpha minus sine alpha, sine alpha, and cosine alpha. And we want to check that AV is equal to W. Okay, so let's do that. So we have cosine alpha minus sine alpha, cosine alpha. And now we're multiplying that with r cosine theta and r sine theta. Okay? And so we want to see what we get. maybe we'll use the regular matrix multiplication method. So when I have a 2 by 2 matrix and I multiply by a 2 by 1 vector, my result is also a 2 by 1 vector, right? Let me just write that down, right? This is 2 by 2. This is 2 by 1. So the result here is also going to be 2 by 1. And what do I get? I just take this matrix, I take the top row of the matrix and dot it with this vector. That gives me the top entry. And I take the bottom row of the matrix and dot it with the vector, and that gives me the bottom entry, right? So what I end up getting here is r cosine theta times cosine alpha. That's this times this. And then it's going to be minus r sine theta sine alpha. So minus r sine theta sine alpha. And then what do I get for the bottom entry? Well, I'm taking the bottom vector and taking the dot product with this vector. So I get sine alpha times r cosine theta. So this is r sine alpha cosine theta. And then now I take this and multiply it by this. I take the cosine alpha, multiply it by the r sine theta. And so I get plus r cosine alpha sine theta. And if you check, you see that these vectors are equal, right? This top entry here is exactly this, r cosine theta cosine alpha minus r sine theta sine alpha. And this bottom entry here is exactly this, r sine theta cosine alpha plus r cosine theta sine alpha, right? I mean, in this case, the orders are reversed, but it's addition, so it doesn't matter that the orders are reversed. So this works. And so what's the upshot? The upshot of this is that the matrix cosine alpha minus sine alpha, cosine alpha represents, or maybe I won't say represents, I'll just say gives rotation counterclockwise. I'll just abbreviate it, right? CCW. So it gives rotation counterclockwise by the angle alpha. Okay. So if we want a matrix that multiplying that by that matrix means that we rotate a vector counterclockwise by the angle alpha, then this matrix is exactly what we want. Okay, because we start with a kind of general vector, which we can write in this polar form, this r cosine theta, r sine theta. And then we see that if we rotate it by alpha, we get this more complicated expression. But in fact, we have a matrix that also gives us the same expression. So that matrix must exactly be rotating the vector by alpha. Okay, so we'll do an example, but before we do the example, any questions? Okay, so let's do an example. Yeah, before we talk about reflections, let's do an example. So I'm just going to recall. Okay, so let me just recall that no, that's not what I want to do. So recall that the matrix, I'll just write it again, cosine alpha minus sine alpha, and cosine alpha rotates vectors counterclockwise by the angle alpha. So a question would be, what is the vector you get by rotating the vector, well, I can just give it, I don't know, 3, 4 through an angle of 30 degrees counterclockwise. Okay, so this would be an example. Okay, so well, what do we do? Well, we need to take, so let me just draw this first of all, right? So we have 3, 4 that maybe looks like this. 3, 4 maybe looks like this. This is 3, 4. And then we rotate it 30 degrees counterclockwise. And then maybe it's something that's really pointing very high up right here. Maybe this is like after 30-degree rotation. Okay, so what do we do? Well, we need to figure out what the matrix is that we're going to use. So we have, so this is the answer. So we let alpha be 30 degrees. So then the matrix is what? Well, we have to fill it in. So cosine of 30 degrees, if you remember, is square root of 3 over 2. Sine of 30 degrees is 1/2. So I have minus 1/2 here. And then sine of 30 degrees is 1/2. And cosine of 30 degrees is square root of 3 over 2. Okay, this is what happens when we plug in alpha equals 30 degrees to this matrix. So now what do? We calculate this matrix, root 3 over 2 minus 1/2, 1/2, root 3 over 2, and we multiply it by the matrix, by the vector 3, 4. And the answer is what? Well, we get 3 cube root of 3 over 2 minus 3 halves. Minus 4 halves. That's what we get for the top entry, right? Because it's 3 times root 3 over 2 minus 1/2 times 4. That's just 2. And in the bottom entry, we get 3 halves minus 4 square root of 3 over 2. Okay. As our vector. And let me just write out in decimals what this actually is. So 3 sqrt 3 divided by 2. Okay, so this up here. Oh, sorry, this is plus. So this up here turns out to be about 0.60. And then the 3 halves plus 4 times square root of 3 over 2, which is 3 halves plus 2 square root of 3. This is going to be 4.96. Okay, so this is the answer here. Okay, so if we take this vector 3, 4 and we rotate it a little further, we get this answer, which makes some sense, right? The x-coordinate's very small because it's almost pointing parallel to the y-axis. And then the y-coordinate is big. It's actually almost the full length of the vector. It's almost 5, right? This vector has magnitude 5. And so this is almost pointing straight up. So we would expect the y-coordinate to be almost 5. Okay, so this is a very reasonable answer for what we're thinking about. Okay, so this, if I told you before, here's the matrix 3, 4, rotated 30 degrees, what are you going to get? That's not that easy a question. But having the matrices makes it easier because you just write down the correct matrix for rotation by 30 degrees and you multiply it by this vector 3, 4. And whatever you end up getting, that's going to be the answer. Okay, are there any questions about how we apply these rotation matrices? Okay, it's clear. No questions? Okay, so we won't have time to do the full rotation unit, but I want to talk a little bit about, to do the full reflection unit, but I want to talk a little bit about some basic reflections. Okay, so question, Bakai? Okay, so we want to talk about these reflections. So we did a rotation matrix. So now we're going to do some reflection matrices that are a little bit easier. So here's a question. What is the matrix that reflects vectors over the x-axis? Okay, so let's say I have some vector v, which is given in coordinates by x, y. Okay? And I want to know, so let me actually make this in two different parts. So this is going to be over the y-axis, and this is going to be over the x-axis. Okay? So let's say I have some v, which is a vector xy, and I want to know, how do you reflect vectors over the x-axis? So, well, drawing the vector, it's going to look like this, right? This is the reflection of v over the x-axis, right? So this is the reflection. And what are going to be the coordinates of this vector? So if I start with xy and I reflect it over the x-axis, what are the new coordinates? Anybody want to answer the question? So xy would go to what?
Yeah,
Yes, Linford?
yeah, it'll be yx.
So let's be a little careful, right? So yx is what happens if you switch the x and the y coordinates. So what you'd get over here by switching the x and y is a vector that's a little bit steeper, but it wouldn't be the full reflection over the x-axis, right? So let's compare. What's the x coordinate of this vector compared to the x coordinate of this vector? What do they have for their x coordinates? Well, they're the same, right? So whatever this vector is, its x coordinate should be the same, right? Because just from the picture, the x coordinate here is the same as the x coordinate here, right? They lie on the same line. Now, what about the y coordinate? We flip this over the y-axis. Oh, sorry, over the x-axis.
Yeah.
So what happens to the y coordinate? Yeah, Linford?
The one, yeah.
Oh, sorry. Sorry, 3.14159. I need to remember your name.
Gabriel,
Right, Gabriel. Yeah,
why would take negative?
exactly. So y is going to go to minus y. Very good.
Yeah.
Okay. And so let me draw the same picture for the y-axis over here. So we start with our vector v, which is equal to xy. And now we reflect this over the y-axis. This is the reflection. So what would the new vector v be here when we reflect it over the y-axis?
Can I try?
Yep. Yeah, Gabriel?
Okay. If we reflect over the y-axis, x value will be negative,
Mm-hmm.
and y value will be, y will remain as y.
Exactly.
Y.
Y would remain as y. Exactly. So one of these takes xy to x minus y, and the other one takes xy to minus xy. Okay. So the question is, what is the matrix that does this? We want a matrix A. So here we want a matrix A so that A times xy is equal to x minus y. And here we want a matrix A where A times xy is equal to minus xy. Okay. And so what do? Well, we have to guess a little bit, right? Well, we know that we've seen before that 1, 0, 0, 1, if we multiply this by xy, we just get xy, right? This we've seen before.
Mm.
But now we don't, let's say we don't want xy, we want x minus y. So what entry in this matrix do we have to change so that instead of y, we end up with minus y? Anybody guess which entry needs to be changed in this matrix to make sure that we end up with minus y?
Hello.
Hello, yes, yes, Gabriel?
Sorry for, okay. The interest that will change here will be the fourth value where
Exactly.
we have, yeah, okay.
And what do we change it to? Instead of a 1, what should we use?
It should be -1.
Exactly, right. So instead, we have to put in a negative over here. And you know what, maybe I'm going to write these in red just to show that if I change the y to -y, then I change the 1 to -1. And you can just check, right? You can just check this is true. Right? If you multiply this matrix 1, 0, 0, -1 by xy, in the top entry, you're going to get 1 times x plus 0 times y. That's x. And in the bottom entry, you're going to get 0 times x plus -1 times y. And that's going to be -y. So this is exactly right. So to do a reflection over the x-axis, you need to use 1, 0, 0, -1. Okay, so this is the matrix that you want. Oh, let me do this in red. Yeah, so the matrix that you want to reflect over the x-axis is 1, 0, 0, -1. Let's do the y-axis. So again, we have that, 1, 0, 0, 1 times, xy is equal to xy. So now let's say we want a minus on the x, which is what reflection over the y-axis is. So what entry needs to be changed in the matrix to get the x to be a -x?
Interest 1, the first interest.
Exactly, right. Thank you. So it needs to be the first entry that's changed. Okay, so if we change the first one to a -1, then it works, right? Because you get -1 times x plus 0 times y. That gives me -x. And 0 times x plus 1 times y, that gives me y. So this tells us that -1, 0, 0, 1 is the matrix of reflection over the y-axis. Okay, so we have over the x-axis and over the y-axis. Questions?
Yes, Bolanju.
Yes, Linford.
Yeah, what I was understanding from the x-axis and the y-axis on the reflection.
Mhm.
So does it mean that when you are working in the axis, the reflection of that axis cannot take the negative? Like for example, the reflection for the x-axis, only the y took the negative. Is it because we were not in the y-axis?
Right. Well, the way you should think about it is that when you reflect over the x-axis, only the y-coordinate changes, right? The x-coordinate stays the same. Now, both of them can be either positive or negative, right? I mean, I drew my vector here, but if I started with a vector where the x-coordinate is negative, then its reflection over the x-axis will still have a negative x-coordinate, right? The point is that the x-coordinate doesn't change, but the y-coordinate does change. It might change from positive to negative, like in this picture, or if I'm down here, it might change from negative to positive. That's fine, but it changes, whereas the x-coordinate stays the same, and it might stay the same as a positive value, like I've drawn here, or if I drew a vector in the second quadrant, then the x value would be negative, and it would stay negative when I reflect it. But the point is the y value changes and the x value doesn't. And when you reflect over the y-axis, then the x value changes, but the y value doesn't. Okay. Does that answer the question?
Yeah, it's
Understood. Thank you.
Great. You're welcome. Okay, so we're basically out of time, so we're not gonna have time to do this. We'll do it next time. But what we want to do next time is to consider the reflection over a line that's not the x-axis. So let's imagine I have a line like this that makes some angle alpha with the positive x-axis. And then I have some vector v here. Maybe I'll draw it in red. If I have some vector v here, and I want to reflect it over this line. So I want to take the mirror image over this line. So here we would have that w is reflection, we'll call the line L. W is the reflection of v over the line L. And the question is, can we find a matrix sorry, I'll be done in 1 minute. So can we find a matrix? Sorry, can we find a matrix that reflects a vector V over the line L? Okay. What we found over here is matrices that reflected a vector V over the x-axis and a matrix that did it over the y-axis. So now if we just have any line, can we find a matrix that reflects the vector V over that line? Okay. And so this is what we're going to talk about next time. We're not going to do these. So this page will be out of the notes. We'll talk about it next time. We'll talk about all this next time. So I think, so I'm going to have to adjust the homework exercises because this homework exercise we didn't get to yet. We didn't cover, so we'll save this for next time. So the one homework exercise will be, so what is the matrix of rotation by 180 degrees counterclockwise? We can use that. We can use our formula for that. And when you get the answer, you'll see that it should look very familiar. And then this third one is, we'll say that if A is a matrix of a reflection through a line L, then A squared, which is going to be I2, is going to be the identity. You know what, even this, since we didn't talk about reflection that much, well, let me just say through either the x-axis or the y-axis. Then when we square it, we're going to get the identity. And so the question is, can we come up with a reason why when I take one of these reflections, I take its matrix and I square it, I get the identity? Why should that be true? Okay, so let me just say notes will be edited to reflect how far we got. Okay, so I'm going to edit the notes before I send them out. Okay, and then an important reminder. So first of all, another reminder, if you have not typed your name yet, please type your name. Please type name if you haven't yet done so. And then the reminder is that next week there will be no class. This is November 25th, no class. This is American Thanksgiving, so there's not going to be class next week. We're going to resume the week after that, which is December 2nd, and we're going to discuss matrix transformations in 3 dimensions. Okay, so but also, and we'll also finish reflections. Okay, so we'll do matrix transformations in 3 dimensions, and we'll also finish reflections. Okay, so so remember, no class next week, and then we will have class in 2 weeks. So we'll talk about that. Okay, any last questions?
Hello?
Hello, yes. Francis?
Yeah, Andrew, thank you very much for the class today. It was very much educated. And I want to appreciate you and I have Liberian formally for your continued effort to making sure that we become empowered educationally so that we will also be like a torch bearer to help our Liberian students to create interest in math and sciences. And I want to appreciate you highly. But I overheard you talking about tapping the name for attendance. Where do we tap the name for attendance? Because immediately when you register.
So there is a chat right here in Zoom, right?
Okay.
So if you, so you should, are you getting the chat messages that are coming up in Zoom? People are typing their name.
Yeah, I've seen the chat messages coming.
So you should be able to just write into the chat. You message everyone.
Okay.
And you should be able to just write your name in and press enter.
All right. Thank you.
So, well, let's see if we want to keep it. Yes, the reflection. So I see a question from, so why not in the next minute, see if you can do that. And there should be a place on Zoom for you to write something into the chat. There's a question from Emmanuel Pena. So the reflection of vectors works with the Cartesian plane. Yes. Yeah, it works with the Cartesian plane, which is what we're doing. And it works with every line that goes through the origin in the Cartesian plane. So we'll see next time that we can find a matrix to reflect over any line at all. Okay. So we'll see that again next time. So Francis, if you can't figure this out, I'll just write it in for you, so that we have a record. Okay. But yeah, you should be able to type. You should be able to type it in somewhere in the Zoom app. I don't know. Maybe somebody can help you with the Zoom app and show you where the chat is. I'm not usually on my phone for this, so I don't really know how to do it on the phone. But it seems like somebody can tell you if you talk to them, because people seem to have figured it out.
No problem.
Okay.
Thank you very
All right.
much.
But in any case, I have your name down, so I have you for the attendance this week. Okay. Any last questions?
Thank you very much.
Yes. You're welcome. Okay. So there's no questions. I think I'll end the session, and have a great weekend and a great week. I hope everybody is well and your families are well, and I look forward to seeing you in 2 weeks. Remember, in 2 weeks. No session next week. Next class is in 2 weeks, and I will send the notes and the recording to the chat later, to the WhatsApp chat later today. Okay. All right. Bye, everyone.
Thank you.
You're welcome.